this is called a graph. So like this can be a possible graph. Let me just call this vertex 1, vertex 2, vertex 3, vertex 4, vertex 5. Or if you're drawing, you can have other graph too, like this one, vertex 1 to vertex 3, then to vertex 2, then this to vertex 5, and these two, and then this to vertex 4. These are called graphs. In this one, your vertices are obviously same, the 5 vertices here and the same 5 vertices here, but your edges have changed, right? So initially V1 vertices in this one. So in this particular instance, your vertices are denoted by this V1 comma V5. So that's one vertex. And V1 comma V2. That's another vertex. V2 comma V3. Then V1 comma V4. And then V1 comma V5.
Ma'am, V1 and V3.
One is extra, right? Yeah, we've written one edge 2 times. This one's done. So we have 4 edges. These are called edges, and when we write them in drawing, we draw them like this, or when we write them in mathematics, they're written in this form: brackets and separated by comma. This is one edge. This is the second edge. This is third edge. This is fourth edge. So in this one, it's V1, V2, then V2, V5, another edge, then V5, V4, V3, V5, and V1, V3. Yeah.
Ma'am,
So
in
in
the
this
first one,
graph, these are the edges.
ma'am, in the first one, we cannot say V1 and V3.
No, V1 and V3 is not an edge. This is called a path. We'll come to that later. Path means when you can reach from V1 to V3. So joining two edges makes a path. Two or more edges when joined together forms a path. That's a path. We have a path from V1 to V3, but that's not called an edge. Edges are direct ones. From V1 to V2, that's an edge. V1 to V3, it's not an edge. Is that okay?
Okay, ma'am, understood.
I'm
Yes,
sorry
ma'am.
to interrupt, ma'am, but I have a doubt that V2 is a middle point.
V2 is middle in the sense it's a vertex here. We have V1 to V2 and then from V2 to V3. These are edges. Was that your doubt or was it something else?
Um, like I'm unable to understand the whole thing. Can you repeat once?
Ma'am, I think she must have seen the V2 as the like it cuts V3. That's what she's thinking about. So she's asking if
It's
it's the
not.
middle point. Yeah.
First, we drew the vertices, right? We first drew the vertices and then this is V2 and what was the other vertex? V3, I guess. So this is one vertex and we draw an edge between them and then this is another edge. If this is V3, then this is another edge. This is not a midpoint of these two. These are vertices. And then if these vertices are somehow related to each other, now that relation you define. Relation depends on the graph. Each time when you take different graphs, the relation changes, right? So as per that relation, you draw if you don't see an edge between V4 and V3, that means as per this relation or whatever relation is there in this graph, V4 and V3 are not related to each other. That's why they don't have an edge. Like a very simple example that you can take is, let's take example of friends. You can say that V1 and V2. So let's take V1, V2, V3, these vertices as people. Let's say these V1, V2, V1 to V5. These are people. And then the edges that you're taking, these edges, V1 to V5. So we have an edge between V1 and V5 or any two vertices if they are friends. So if V1 and V5 are friends, then they have an edge. V5 and V4, they do not have an edge. That means they're not friends. So that's one way. Your edges represent the friendship here. Edges are for friendships. And your vertices are people here. That was the relation that I was talking about. So edges here, the relation they represent is the friendship relation. It could be any other relation. So that's your graph. Now this one
Got
is
it,
called
ma'am.
then, sorry, what?
Got it, ma'am. Thank you.
In this particular example, there's no midpointing. It's just basically V1 to V2. That means V1 and V2 are friends. You have an edge between V2 and V3. That means V2 and V3 are friends. No edge between V3 and V4. That means V3 and V4 are not friends. And there are two types of graphs. One is a directed graph and the other one is an undirected graph. So in a directed graph, you have directions. Like in this one, we have not drawn directions, right? When we draw an edge between V1 and V4, it's not directed. It's just a simple edge. But when you take things like this, V1, V2, and V3, and then you add directions to this graph, then it's called a directed graph. Direction in the sense this one and this one. You can take here a simple example of a directed graph. So this one that we drew initially for the friendship one was an undirected graph. This is an undirected graph. This one's also an undirected graph. And when you see arrows here, it's called a directed graph. And what could be an example of it? Again, we should, let's just take people here. And then instead of this thing, let's take that if this is an arrow, that means this edge represents that B1, this one. So if this is A and this is B, then A is brother of B, right? You can take this thing. This is a directed graph because you have directions here, right? If A is a brother, initially when we had this thing, if V1 is a friend of V2, that means V2 is also a friend of V1, right? Friendship goes both ways. But your relation of a brother sister, it doesn't go both ways because if A is a brother of B, that doesn't mean B is also a brother of A. It could be a sister, right? So so by that logic, this direction thing holds here. This one in this example, you should be taking in this example of a when you take instances of brother and all, you should be taking a directed graph, right? Directed graph works better here. So that's the difference between a directed graph and undirected graph, which is simply just the arrow. And when you have to go both ways, if you have something like this, V1 to V2 and V2 to V1, that means V1 is a brother of V2. V2 is also a brother of V1. That means these are both males and they are brothers or siblings. Both works here. Because they're okay. Is this part clear?
Yes, ma'am, clear.
Yes, ma'am.
Okay. And this graph we denote by G and it's written in this form, VE, where V are vertices and E are edges. Then we'll come to the applications of graph and graph theory. So first application is your graph coloring problem. What's a graph coloring problem? In a graph coloring problem, what you do is, the simple example is a map of India where the states are mentioned, right? So when you take map of India, let's say you can, if the states share boundaries, let's say you have map of India and the states that share boundaries, they cannot have the same color. You have to color that graph, you have to color states in that graph, but you can't color two states that share a boundary with the same color. So if, for example, Haryana and Punjab share boundaries, right? So you shouldn't be coloring these two with the same color. So in that way, you will be coloring, like, let's say you have states here. This is state one, this is state two, this is state three. So what you do is, how do you draw a graph? You're marking the states here. And then now your vertices are, in this case, your vertices will be states, right? And your edges will be, now there'll be an edge if they share a boundary. Or I should be writing edge exists if these two states share a boundary, right? That's what your edges represent. Like if this is one state and this is another state, and you see an edge here, that means these two states share boundaries. And these two, so you can, instead of having the complete map of India, you can just have the vertices as states, and then you can connect the states or vertices. If they have, if they share a boundary, then draw an edge. If they don't share a boundary, don't draw an edge. So if you see things like this, that means these two share a boundary, these two don't. I hope you understood the graph, right? So in graph coloring problem, what you do is you need to, and what's our problem? Our problem is that we need to color each state, but we have to make sure that no two states that share a boundary are colored with the same color. That means if you're coloring one thing, if you're coloring V1 as blue, let's say, then V2 you shouldn't be coloring with blue color because they share a boundary, right? So if this is one state, this is another state, they share a boundary, then you shouldn't be, if you're coloring this as blue, you shouldn't color this as blue because otherwise the states won't even be visible on the map, right? They would look like one state only.
Ma'am, I have a doubt.
Yes.
So V1 and V2 are the points, and we have to color them with different color so that we know that they are different. And isn't it? Or we have to like color the boundary with the different color.
No, if you have, it's a simple example of you have a graph of India, and let's say these states, these are the states, and that now these three states share boundaries, right? And if you have this state too, then this state does not share a boundary with this one, right? In fact, this doesn't share a boundary with this one either. So if you have this thing, let's say this is V1, this is V2, this is V3, and this is V4. And as per the graph, it should be V1 shares a boundary with V2. So you should have an edge between. And should it be a directed graph or an undirected graph? We've discussed the graphs, right? So should it be a directed graph or an undirected graph in this case?
Undirected.
Yeah, it should be an undirected graph. So V1 and V2, they share a boundary, so there should be an edge. Then from V2 to V4, there should be an edge. From V2 to V3, there should be an edge. And V3 to V1, there should be an edge. So this should be the graph representation, right? Now, if I have to fill this one, like see this as a map. Now, if you have to color this, let's say you're coloring this blue, and if I color this, my aim is to color the one that share a boundary. Now, the states that share a boundary, they should be colored with different colors. For what reasons? That's not important. Why are we coloring them with different colors? That's not important. The important thing is that our aim is to color adjacent states with different colors. That's all. So if V1 and V2, because these two are adjacent states, so we should be coloring them with different colors. So if you've chosen blue for V1, then V2 you should choose different colors. So you should choose green here, some other color. Then for V4, now V4 I can't choose, what color can I not choose for V4? V2 is already colored green, so I cannot choose green for V4, right? But I can choose blue again for V4, right? Because V1 and V4 are not adjacent states. They don't share a boundary. That means you can use the same color for V1 and V4. And then V3, it shares a boundary with V2.
Ma'am, can you just describe it with using a color so that we can learn it more easily? It will be more convenient.
Yeah, okay, we'll do that. Let's say I've chosen blue color, blue's here. And I'm using blue color for this state. Now I fill the entire thing with blue color.
Ma'am, in the vector sense, like as you have drawn the edges, there you can use the color, so we'll end there.
Where? Here?
Yeah, edges.
Okay. Let's do this one as we're not coloring the edges. We're just coloring the vertices, coloring the states here, right? So we're coloring this blue. Let's mark this blue, right? Then now V1 and V4 do not share an edge. That means they don't share boundaries. So you can color this one blue and you can color this one as blue, right?
Yeah.
And coming to V2. Now V2 is adjacent to obviously V1. So you should be using different colors. So let's use green here. And let's use green for this one. Now you can't use green for V3, can't use blue for V3 because it's adjacent to both of these. So you should be choosing a third color, right? Let's choose
Like red.
This one we'll use red. Is that okay? If you had more states here in the graph, then you do things accordingly. Like let's say if you have V5 here, then you have V6 here, then you have V7 here.
Ma'am, just one thing.
Yes.
Just because V3 is not adjacent to V4, so that red color I can also apply to V4 also, right?
You don't need to. When you start with the graph here, we started with V1, right? So we use blue color here. You can use red here, but that's of no use. We're trying to use minimum colors. Our aim is to use minimum colors. Otherwise, we can use different colors for different vertices, right?
No, ma'am, I
That
was
will be the
asking that
easiest.
V3 and V4 are not adjacent, right?
Yeah,
So we can use same color for V3 and V4 as well, right?
yeah. You can use red for this one. If
Oh,
you're
okay,
saying
ma'am.
you can use red for V4. That's fine.
Yeah, ma'am. Yeah, I was asking that. Yeah, okay.
Okay.
Understood, ma'am.
Now for this one, because V5 is adjacent to this, so you should be using can't use blue, so you can use red and green. Let's use red in this one. You can use red here, and then again you can use. Now you can't use red here, can't use blue here, so you should be using green here. And same the and with this one you can't use red. And if this was also connected, let's say this is connected to these two, then you can't use red, can't use, or if this is connected to this too, then you can't use any of these three colors, right? You can't use blue, can't use red, can't use green. So you should be using, let's say you're using white. Use white for this one. Is that okay? That's your
Yes,
graph
ma'am.
coloring
Clear.
problem where you choose colors in such a way that each vertex and every vertices that are connected to each other have different colors. That's your graph coloring problem. It can be expressed in different words too. So the other way it could be phrased is, let's take another example.
Ma'am, these arrows are,
So
ma'am, these arrows are edges, na?
these ones, or
Yeah, the
these
way they are
ones,
connected. Yeah, ma'am.
these ones are, yeah, these ones are edges. Okay, then another example for graph coloring could be the date sheet thing. So let's say you have subjects and let's go back to your 12th standard where you had streams and you had different subjects. So we know that usually there's no such rule, but usually some subjects are not offered together, right? Like if you have, let's say you have economics, then economics is not generally offered with physics, right? And it can be in some schools, but we're talking in general. So uh, usually they are not offered together. And then chemistry is there, and let's take biology too. Let's take maths too, and then let's take Hindi, English, and let's take these subjects. So when you have these subjects, and let's take history too. So when you have these subjects, and you want to conduct exams of all these subjects. So you can't be connected because these two, physics and chemistry, some students will be choosing simultaneously, right? Some students would have both physics and chemistry as their subject. So you cannot have the exam of physics and chemistry on the same day, right? So if you are to make a date sheet, then what do you have to do? And you have to get done with the exams. You want to get done with the exams as quickly as possible. So you need least number of days. So how do you decide those days? Those days are the same as colors that we use in the above graph, right? Like let's say you have economics here, and let's just take a graph that this is English, let's say. In English, you can opt with economics. So there could be students. So these vertices here are subjects. In this particular case, your vertices are subjects. and your edges are, so there is an edge between two vertices V1 and V2. If a student has opted for both subjects, or if there is an option to opt for V1 and V2 both, right? So economics and English can be opted together. There are students who choose these two subject combinations, and then we have Hindi that can be opted to with economics. Then we have history that can be opted to with economics. Then we have physics. Physics is generally not opted with physics. So physics here. Then chemistry, maths, and then we have biology. So biology is, it can be opted with these subjects, right? And then it can be opted with English too. And it can be opted with Hindi too, right? So if this is your graph, let's say, then if you'll color, and now you have to decide days. So let's say you're conducting the exam of English on Monday. That's the same as giving a color to English, right? So let's say,
Just one thing, ma'am.
yeah,
You have connected English with biology, but you have not connected English with maths or like chemistry.
yeah,
But
yeah, you can connect it. It's connected to all of these. I don't want this graph to be very
yeah, yeah,
messy.
got
That's
it,
why I'm
got it.
not connected it.
Yeah, okay.
So you can connect. We are just trying to have this common. Let's just have it this way. Okay. So for English, let's say you've decided the 1st of December, first date you've chosen for English. Then you can't have the exam of economics on that 1st December. English and Hindi, let's say you can opt together. So also Hindi's exam also you can't have on the same day. Let's say history and English can't be opted together. Let's if these two actually have edges, then this should have an edge actually. In this particular example, if these two have an edge, then this two should have an edge, right? But for now, for simplicity, let's just say that this does not have an edge. This is just for you people to understand, but technically there should be an edge between English and Hindi in history, because there's an edge between English and economics and history. So that way there should be an edge between English and history too, by logic, but let's just not go that way. Let's just stick to this graph only. And on first, you can have the exam of this. You
Ma'am,
can't
what
have
was
the
the
exam of,
last logic you said? If the like what we have to ignore, suppose there is no edge between English and history, you are saying that.
yeah, there should be an edge between these two, right? Because if you have an edge between English and economics, that means you can opt these two subjects together. And there's an edge between these two, that means you can opt these two subjects together. That means you can opt English and history together too, right? But let's not go there. Let's stick to this graph only. Then on first, let's say you're having the exam of English. You can't have the exam of history on first, so you should be having it on second. Can't have the exam of economics on first and second, so you should be having this on third. And in this one, you can't have the exam of this on, there's no edge between these two, right? And there's no edge between these two either. So you can have it on first or second. So this you can have on first or second. Let's just assign this first. And coming to this one, you can't have the exam of this on first. You can have it on second or third, right? This one, physics one. So let's have it on second. Now these are all connected to each other. So this you have on second. This one you should have on third or first. This one, because you've taken third here, second here, both are connected to this. So you can't take second here, third here. So you should be taking first. And then in this one, you can't take first because it's directly connected to B. Third is also, this is also directly connected. This is also directly connected. So you should be taking fourth here. Is that okay?
Ma'am, can we say that this first, second, third, fourth are colors?
Yeah, these are colors only. But
Okay,
in
okay.
this particular example, That's why I write these things. Your vertices are subjects, edges are this thing, and then this color is nothing but your dates. Treat dates as colors in this only. Okay.
No, no, no doubt here.
Yeah.
Isn't this same? I can't find the difference between this and the independent set. Is this the same
What?
as independent set?
Same as what?
Independent set problem in graph theory.
Yeah, we'll come to that. We'll come to
What
independent
is the
one. Yeah,
difference
we'll come
between
to
this
that.
and this?
We'll discuss
Okay.
this in a while. And then
Okay.
we'll discuss what's the difference. This is your graph coloring problem. And then next up we have vertex cover. So our second application of graph theory is vertex cover. So vertex cover is basically, V is the collection of vertices, right? Like if you have 5 vertices, then you write all the vertices there, V1, V2, V3. This is a set. And then in vertex cover, this vertex cover, let me just call this C. This is a subset of V. So in vertex cover, what vertices do you take? Let's just take a graph, or let's just take the above graph only. If we consider this graph, then the vertex cover should be, vertex cover means that you need to cover every vertex cover is basically a set. Let me just first write the definition of it, and then I'm not writing the definition, I'm just letting you know what the definition is. So the definition for vertex cover is it's a subset of the set of vertices. And what type of subset is it? It collects all the vertices such that if you have this graph, then from each edge there should be at least one vertex. So if you have C here, C is a vertex cover of this graph. Let me just call this graph G. Then C, it's a subset of V, is a vertex cover of your graph G. If in this graph you have edges, right? This is EP is an edge. So for every edge, there should be at least one vertex present in this. Then we say that it's a vertex cover. For example, let's you have this graph. Then if you need to find the vertex cover for this graph, then the cover should be, let's start from this edge. What's our aim? We need to collect vertices in such a manner that from each edge you have one vertex in this cover, right? So from this edge, let's take E. From this edge also, you have one vertex E, so you don't need to consider the second edge. Then this third edge, you need to have one vertex, so let's have H. From this one, you need to have one, so let's have this one. Or what you could have done is you could have directly taken you could have taken economics. So that covers a lot of other edges, right? So if you choose this one, it covers this edge, and covers this edge. So now these three are covered. You don't have to worry about these three edges. Coming to this one, you can choose one vertex from this edge. So let's take E. And then from this edge too, you need one. So you've already chosen E. This is also covered, right? And coming to this one, you need one. Let's choose C. Now in this one also, because you have chosen C, so this edge is also covered, right? And then in this edge, you need one. So either you'll have to have P or B. So if I have P here, then this one's covered because you have one vertex from this edge, P. And or let's have M instead. Because if you will have M, then you'll have one from this edge and one from this edge too. And one from this edge too. So now everything is covered, right? So our aim is from each edge, you need one vertex. That's all. That's your vertex cover. So this should be the vertex cover, right?
Ma'am, even if we would have taken P, it would have covered MC and B, na?
It would have covered this one, this one, this one.
Yes, ma'am.
But then this is, you need one from this one too, right?
Okay, 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 okay.
M you will have to take. And we have not taken P here actually.
Can you repeat this vector vertex cover again?
Yeah, let's do
Because
it with
it is,
some other graph.
it is
Let's say
stating
you have
like
this graph.
Ma'am, a
it is
doubt in the
stating
previous one.
it is
Yeah.
stating like vertex cover, but why we are uh, choosing edges? So why we are covering edges?
Our aim is, so first thing that you have to remember is your vertex cover is a subset of the set of vertices, right? So it's a subset of this. So you have to collect vertices in such a way that from each edge, there is one vertex present in your vertex cover. So if this is your vertex cover, from each edge, you want one vertex to be there in the vertex cover. So like in this one, from this edge, you need one. So either choose V5 or V2 because V2 covers more vertices. Now in this particular case, V2 covers all. If you choose V2 here, then you're done because it covers this edge, covers this edge, covers this edge, and covers this edge too. Now if you
Okay,
have this edge,
from each edges we need
yeah,
to specify one vertex.
one vertex, right? So
Ma'am,
if you
I
have
have
this
a
thing,
point
yeah,
in the previous one actually.
1 second. Yep.
So in the vertex HB, do we have to take like one node, like from H or either B, or it's covered?
From B, B is covered, no? You have chosen C. So CB, you have you have to look at edges. You have one edge CB. So from there, actually B's P and B are also related to each other. So you should have one of these. So you should have either P or B for this edge to be covered.
And ma'am, what about HB, the one that's outer one?
Which outer one?
The
Okay, we have
yeah.
we have these two too, right? Thanks. We have these two too. So from B and H, let's
We'll
have
take
B
B
here.
instead of P.
If you will
Yes.
take B, everything is covered.
Okay, got it.
That's your vertex cover. It's usually used for, let's say you have one example for this is, now you can take these as corridors, your edges to be corridors and these to be CCTV cameras. So to cover this entire corridor, it's enough to have a CCTV camera here, right? So if you have a CCTV camera here, it covers this one, this corridor, it covers this too, and it covers this too, right? So all of these three corridors are covered then, and this one too. Then you should be worried about these two corridors, V3, V4, and V3, V6. For that, you can install a CCTV here. So you just need CCTVs at these two vertices, V2 and V3. And all the corridors are covered. That's one application of this one. Is that okay? Can we move to the next topic?
Sure, ma'am.
Okay.
Ma'am, one example.
Let's say you can have, yeah,
Just explain one more example for vertex cover.
okay.
Ma'am,
Let's say your,
in the last example, you said V2 and V3, they are like, we choose this, but V2 and V3 are also connected, na? We have to take from one, na?
you don't have to take exactly one. Our idea is from each edge, you should have one.
Okay, okay.
We don't mean that we only should have one from each edge. You can have two from an edge, but make sure that from each edge you have one vertex. That's all.
I thought if two vertices are connected by one edge, we have to take at least one from the
Yeah,
two.
you have to take at least one.
But here V2 and V3 are connected. Those are two adjacent vertices, so we should have taken one from that. Is it?
At least one means you should take one or more, right? So you can take,
Okay.
that's what at least means, right? So other example could be, let's say let's say there's a product and you are selling that product, and you need to make sure that there's a group of people that just represent these people by these V1, V2, V3, and V4 and V5. So you need to make sure that your product is advertised to every person, or every person knows about your product. So if this person knows And we're assuming that if one person knows, that they're going to tell their friends too. So this is an assumption that we're making here. And if now these are people, and this represents friendship between them. So the edges here are again friendship or any relation between these two people. So if these two people are related to each other, we're assuming that if they're related to each other, they're going to tell each other about the product. So if these two are related, let's say these two are also related, this, and then let's say this one. Then you need to find the maximum number, the minimum number of people or the people that you should be telling to make sure that everyone knows about your product, right? So let's start with this one. If you'll tell this person, V2, and in this one, our main idea is maximum you can tell everyone, right? If you have to cover, maximum such set could be take all the vertices. So maximum could be V1, V2, V3, V5, V4, V5. That's the maximum set possible to cover all edges, right? But we don't need that. We're more interested in finding the minimum set or the set that
Ma'am,
contains these number of, yeah.
will the number of vertex covers will change if we
Yeah,
change the
it'll
initial one?
change.
Okay.
It'll change. Like we just discussed V1, V2, V3, V4, V5 is a vertex cover of this, but we don't want that because it's a
Okay.
trivial one, right?
So if we want to find the minimum one,
Yeah,
how
we're
will we
interested
find
in the
it? Like,
minimum.
so is there an equation or something, or else
No,
we have
no,
to
we
do
don't have an
everything on it,
equation.
right?
No,
So
you
we have
start
to
with this
find.
one. The one idea that you can have is find the start with the vertex which is connected to the most vertices. So this one here is connected to most vertices, connected to 3 vertices here.
Okay.
Include this one
Okay.
to ensure that it reaches the maximum number of vertices, right?
Okay, ma'am.
When you take this one, this one, this one, and this one is already covered. Now you just have to worry about this edge is covered, this edge is covered, this edge is also covered. So you only have to worry about this edge. This is better.
Yeah, so
Go
we'll
ahead.
take V4.
Yeah, take V4 or V5. Both work.
Can't we take V3?
V3 is not here. It's here.
Okay.
Ma'am, if vertexes keep increasing means this cover also keep changes, right?
Yeah.
Okay.
Okay. Can we move to the next topic? That's independent sets.
Ma'am, as he
Yeah.
asked, as the vertex keeps adding, it's not necessary that the vertex cover also increases, right?
It's not necessary. It depends on the graph.
Exactly. Yes. Thank you,
Now,
ma'am.
if I'll take a vertex here, V6, now it's not going to change. It
Yes.
might
Thank you so
change,
much, ma'am.
depends
Yes,
on the
yes.
graph.
Yes, yes, yes. I just wanted to confirm that. Yes. Thank you, ma'am.
Okay. Then coming to independent sets. Independent sets need this. Let's take one example for this to understand this thing better. Definition wise, it means if you have a graph, let's say you have V1, V2, V3, and V4. You just have to collect a set. So it's again a collection, it's a subset of this independent set. Let's just call it I. This is again a subset of vertices. V is a set of vertices, set of all vertices, right? So your I independent set is a vertex, is a subset of V. What kind of subset is this? You collect all the edges in this which are not related to each other. In the sense, if you have this thing and then you have V5 here, V6. So if you start from V1, now you put it here. First, you can choose anyone because that's obviously independent of everything else, right? So V1 you can choose here, or you can choose any other vertex. You can start from any vertex. If I've chosen V1, I can't choose V3 because V1 and V3 are not independent of each other. They're somehow related to each other, right? I don't know what the relation here is, but there's an edge that means they're related. So I shouldn't be taking V3. And I can take V6 because V1 and V6 are not related, right? You can take V6 here. You can take V4
Ma'am,
too. Yeah.
we can take V5, like V3, which is not connected with V1, right?
Yeah, you can take all of these. So that's what we do here. Like in the previous one, our aim is to find the minimum such set, right? Here, our aim is to find maximum such set. Maximum in the sense you start with V1, V6 you can include, V4 you can include, V5 you can include, V2 you can include.
Ma'am, aren't V5 and V6 connected here?
V5 and V6, how are they connected? They don't have an edge.
Okay.
When I say connected, I mean, okay, we'll use two terms
Ma'am,
here.
but
One is,
V2 is connected now.
Yes, madam. V2 is connected, right?
yeah,
From the
Yeah,
left.
V2 is connected V4.
V1, V6, V5, and V4 is fine. Yeah. So this set then.
Ma'am, so we are saying that with respect to V1, right?
Yeah.
So if we
With
take
not
V2
with
and
respect to
hold,
V1. Independent set is not with respect to any vertex. It's just a set of vertices which are not related to each other, not directly connected to each other.
okay, so we are not
So
comparing it with V1 and then adding it.
No. That's not what we're
ma'am,
doing. You
it can be indirectly connected, right? It
yeah,
can
indirectly
be
connected you can take.
Ma'am, I think
Yeah,
V1
okay.
is connected to V2, right?
So we have not taken V2 here.
Okay. Oh, okay, ma'am.
This is another set we're considering. So V2 you can't take V4 here, can't take V1. You can take V3, you can take V6, and you can take V4. And actually, in independent sets, just one second. I think I've
We can say it is a 8 set.
V1, then if you're taking V6, you not just have to make sure that it's not connected to V1 directly, also make sure that there's no edge. So it typically means there should be no edge between the the vertices included in this set. That means V1 and V6 should not have an edge. Then you can have V5 because V6, V5, and V1. None of these have an edge with each other. Then you can have V4 too. Yeah, V4 does not have an edge. Okay, in this one it works fine. So in the other one, let's take V2. Now you take V2, can't take V4, V1, so you can take V3. Now you can't take V5 and V6 either. V5 and V6 are not connected to V1, V2 directly, but they're connected to V3, right? So this should be the independent set then.
So I have a doubt. Like, can we take minimum number of which cover everything, or we have to take that maximum number of vertices?
You have to, in this particular case, consider this as we'll do a real life example on this and how do we interpret this entire situation. But what we're doing here is trying to collect maximum number of vertices such that they don't have any relation between them. And when I say relation, I mean they don't have a direct edge between them. So collect
Like
all
in
the
the
vertices.
like in
Yeah.
the vertices cover, we have chosen the minimum number of vertices which are connected with each other. So here we have to choose maximum number of vertices which are not connected with each other, right?
Yeah. In this particular thing, in independent sets, you start with any vertex of your choice and just make sure that every vertex that you add here is not connected to that vertex. So V6 should not be connected to V1. And then when you add V5, make sure V5 is not connected to V1 and it's not connected to V6 directly. That means V6, V5 should not be an edge. V1, V5 should not be an edge. So there should be no edge between the vertices in this set. That's your independent set. And find maximum such set.
Okay, so I have the only I have the doubt in maximum and minimum thing. Like we have to take the maximum number here, and in the earlier vertex corner, we have to take the minimum number.
So when I say minimum and maximum, I don't mean you have to. Independent set only even if I'll take V1, V6, and V5, that's also an independent set. But it's not generally the questions are based on maximal independent set. That is of practical use. That's why I'm mentioning the maximum thing here. This is also an independent set.
So in a way, V1,
Oh,
V6, V5, and V4 is more of a practical application of this
yeah,
because
we'll
it
do
has
an
maximum.
example on this. Yeah,
Because
then you'll
it
be
has
able to
maximum.
see. Yeah.
Madam, can we do this for V3 so it will be more clear? Because that is the most connected edge. So
Yeah, let's do it for V3. When you start with V3, you can't take V6, V5, can't take
V1.
V2, V1, and then you can take V2, right? So take V2, and then you can't take V4. This can be an independent set, or V3, V4 can be an independent set. Both work.
V3, V2, and
These are
V4
actually,
also.
Okay.
V3, V2,
so
and
these
V4.
are only independent sets, right? This is independent. This is also an independent set. this one is the maximal independent set of this one. Maximal means no other vertex can be added to this one to make it. Now, if you'll add one more, when I say maximal independent set, I mean if you'll add one more vertex to this independent set, then it won't be an independent set anymore, right? If to this set I'll add one more vertex, then it's no longer an independent set. But if to this set I'll add one more vertex, it can still be independent. This one, I can add v4 to this and it's still independent, right?
Ma'am, in the above right, you were just a little above in the right. You were trying to reach a topic here. What was that?
Yeah.
Reachable? Yeah. Can
Yeah, I
you?
was talking about reachability and the one is reachable and the other one is directly connected. That means they have an edge. So when I say connected, I mean they have an edge. Although connected is like a literal term that's used in graph theory. So let's not use connected that often. But when in that's an informal term that I'm using here. Connected. When I say these are connected, that I shouldn't be saying that, but it's just easier. That's why I say these two are connected. Actually, I mean that they have an edge. When I say V1, V2 are connected, I mean they have an edge. Or when I say they're directly connected, I mean they have an edge. Is that okay? And reachability means what points can you reach? So when I say directly connected, I mean they have a direct edge. I don't mean that you can reach from here to here. Obviously, you can reach from V1 to V4. That's about reachability. But when I say, or when I talk about directly connected, I don't mean V1 and V4 because they're not directly connected, right?
So, ma'am,
A
reachability
very
This
nice
doesn't.
example
terminology
could
I
be,
wanted to make clear.
Ma'am, reachable doesn't mean directly connected, na?
No,
Okay.
no, reachable just means that you can reach from here to here. Like from V1 to this point, you can reach, right?
ma'am, we could think about this as airports, right? Where we like it
Yeah,
is
yeah,
reachable. Yeah, like we need to reach to a certain place, but the only way to go is by a directed like a connected flight.
yeah.
Yeah.
Okay,
So
let's come.
reachability means only the connection of vertices.
Yeah, it means if I say V1 and
Yeah,
V4 is
they
reachable
have
from
the
V1,
edges.
yeah, that means there are edges from you can go from there could be a direct edge. When I say V1 and V4 is reachable from V1, I mean there either is a direct edge from V1 to V4 or there are vertices in between VI, then VI to VI2, then VI3, and then finally you can reach to V4. That's what we mean when we
There
say
exists a
reachable.
path.
Yeah,
Yeah, path.
path is this one, and path I was avoiding because we've not discussed what a path is. Path means this when you have a way to reach from this point to this point. So there's a path between V1 and V4 because you can reach from here to here, V1 to V4. This
In a way,
is,
that is reachability only, na?
yeah, this is called path. So V1 to V2, V2 to V3 is a path, and V1 to V2 is an edge. Okay, then coming to the example that I was going to discuss for this independent sets. Let's say you have to attend classes and you have maths class, then English class, then some other class. Let's say you have physics class, chemistry class, and history class. Let's say you have these classes, and we've decided the times for these are obviously decided. So let's say your maths class is from 10 a.m. to 11 a.m. and then your English class is from 10:15 to 11:15, and physics is from 11 to 12, and this is from 12 to 1, and history is from, let's say, 11:30 to 12:30. Now, if you want to attend all these classes, or let's say I want to find what are the maximum number of classes I can attend, right? I can't obviously attend all of them because there
We
are
can attend 3 of them.
yeah. So if we need to find how many of them we can attend, we should be using independent set theory here, right? Because we start with M. So let's just make a graph first. This one's very easy, so you can just directly see from here. But let's say M, so vertices in this case we're taking subjects E, P, C, H, and edges we are taking. So there's an edge between two subjects if they have the class at same time, or if they have the class at overlapping times. So 10 and 11 and 10:15 to 11:15. So these have overlapping times. So let's have an edge here. So there's an edge here. Then from E to uh, there's an edge here too, from E to P. And then we have an edge from this one, H 11:30. 11:30 is here, right? 11:30 and 12:30. So it should have an edge with C and P. I think those are the only edges, right? And we've not missed any other edge.
E and H.
Yeah, ma'am. E and H.
E and yeah, E and H also have an edge. So this is it.
Ma'am, how will E and H have? It's 11:15 and this one starts at 11:30.
Oh, okay, thanks. This does not have an edge. Let's just
Oh, I thought
let's take
it
it
is on
from
10:30.
35. So if this is your graph, then and if you want to find the maximum number of classes you can attend. So if you start with the maths one, now our intuition should be to start with the subject that is connected to the least number of subjects, right? Because if you start with E, then obviously you can't attend M, P, and H, right? Don't start with the one that's connected to the most. Start with the one that's connected to the least. So start with M, then you can attend this one too, P1. You can't attend E, can't attend H, then you can attend C. So these classes you can attend, right?
Ma'am, we have to
If you
start with
start with
the
E,
ma'am, we have to start with the minimum connected to make it a maximum independent center.
yeah, if you need to find the maximum number of classes you can attend, then it should be 3. Otherwise, if you start with E, that's the most connected subject, right? So you can't take M, P, H. These are obviously already out. Then you can only take C. Same if you start with H. These 3 you obviously can't take, so you can only take M. If you start with C, you'll end up here only. You can take C and E too, but to make it maximum, you should be taking P and M. Is that okay?
So it's like inversely connected. If you start with the maximum, you'll get the minimum ones, and if you start with the minimum ones, you get the maximum numbers.
Ma'am,
Yeah.
if we start with C, we can also have like E and M. We can
You'll
attend that.
start with P, you can't have E then because they have
No,
an
no,
edge.
no.
You can have
I said C. C. We start with C, then we can attend M as also E.
M and E have an edge, so you can't have M and E both here, right?
Okay.
If you start with C, you'll end up with this set only.
Ma'am, how is this different from coloring problem?
It's not actually different from coloring problem. In coloring problem, what you do is you color this. Now this entire set you can color the same, right?
On the
These are
same,
not,
yeah.
yeah.
So
You can
both
use
are
the same
same
color for
problem
this.
only.
They're same only, but they emphasize on different things, right? This emphasizes on the independent set. They're more or less same only, actually.
Okay.
Ma'am, can
This
we
one
say that
emphasizes on independent set, and that other one with graph coloring thing, it emphasizes on not actually the set. It emphasizes on what different things you take. You can take that to be same as well. That's fine. Yes. Anything else?
ma'am, can we say that there
Uh,
is only one maximum independent set in a graph? Like one unique.
No, no, there's not one. When I say maximal independent set, we mean the set that, okay, if you've been given the maximum number of classes you can attend, then there are obviously 3. In this particular case, there are 3 only. And if your question is phrased in such way that you need to find the maximum number of classes that you can attend, then obviously there can be only one answer to it. But if you are just asked, there's a difference between maximal set and maximum set. So this one's a maximum set. Maximum in the sense the 3 will be maximum here. Now you can't top it. But if you have a maximal thing, that means it's independent. This one's independent, but one more added to this set. If you'll add one more vertex to this set, then it won't be an independent set anymore. That's what you call maximal independent set. The same goes here. Now this is already a maximal independent set. This is also a maximal independent. Maximal, I'm saying. Maximal independent set, because if you put one more element here, then it won't be independent anymore.
What is the difference
So,
between maximal and maximum?
That's not important.
ma'am, so you're
Now, what
saying
is the
that,
meaning of the term maximal?
That's also not important. I just discussed this
ma'am,
because I know this thing, and it's
so
not,
if you
you
just,
won't be asked such things.
so we can say that the maximal set will be a subset of the maximum set.
Yeah, maximum in the sense, okay, when you will be asked questions, you will be asked questions on real life problems. So, like in this one, you could figure out that you have to find the set with maximum number of elements that are not connected to each other, right? Maximum vertices that do
Okay,
not have a direct edge. So
okay,
here it could be 3 only. Now you can't have 4. If you can have 4, then you can't have 3. That's what maximum means, right? You can have only one maximum. So for you can forget about the maximal thing.
okay.
It's not needed here. And the other topic you have is matching. So right till now we were discussing the subsets of vertices set, right? V was a set of vertices, and we were discussing about the subsets of this. Now we'll be discussing the subset of E, where E is the collection of edges, like this one, V1, V2. These were edges, right? So this is your set of edges in a graph. So your matching is a subset of set of edges. And what kind of edges do you collect here? So let's say this is M. So M is a subset of E, and what type of so this is a subset, right? You will be collecting edges here. And what type of edges should you be collecting? The ones that are mutually disjoint. Mutually disjoint means if you have two edges, then they shouldn't be sharing a vertex. Like if you have this thing, V1, V2, V3, and if you've written V1, V2 here, then you can't write V2, V3 because V2 and V3 share a vertex. And if you have V3 to V4, then you can write V3, V4 here. That's fine. Let's do a proper example, a proper graph, and then see how your matching works. Matching means for it's a subset of the set of edges where the edges that you collect are disjoint to each other, to every other edge in the matching. So if there are
Means
edges,
intersection should not be there.
yeah, intersection means there should be no common edges, no common vertices between edges. Like between these
Okay,
two edges, you don't have a common vertex. V2
okay,
is not common, V1 is also not common. Nothing, no vertex is common here, right? So let's say you have V1, then V2, V3, V4, V5, and V6. Now, in this particular case, I start with, let's say, you can start from wherever you want. If I take V1 to V2, then I can't take V2 to V3 because there's a common vertex here, right? But I can take V3 to V4 because they don't have a common vertex. Then I can't take V4 to V5. And if you had this thing too, I can't take V4 to V5. That would be incorrect. And I can't take V2 to V5. That's also incorrect, right? Because V2 you already have here, V4 you already have here. You can't take these things. Then you should be
So we
taking
can
V5
only
and
take
V6.
V5 and V6.
Yeah.
Ma'am, in this also we have to choose maximum matching.
No, maximum matching and all will come to, but you just have to choose a match. Matching means now if this is a matching, this one's also a matching. Obviously, if you remove this element, then it's also a matching. right? And this is a very particular example. You can even change this thing. So if I start with V2, I can have V2, V4, or V2, sorry, V2, V3. Then I can have V4, V5. Now this is also a matching, right? Although two elements are left, V1 and V6 are left alone, but this is still a matching. So this is a matching. This is also a matching. If I'll remove one of the elements from here, that's also a matching. This is what your matching means. Matching basically is a subset of the collection of your edges, where each edge, you collect edges here. And what type of edges? The edges that do not have any vertex in common. That type of edges you collect in matching. Is that okay?
Yes, ma'am.
Yes,
And
ma'am.
then right after this, you
Ma'am,
have perfect matching.
we basically use the non-matching ones, right?
Non-matching ones in the sense.
Like you just said that, like for example, V1 and V2. So another pair which should not contain V1 and V2, we are doing that, right?
Yeah.
Okay.
Okay. And then we have perfect matching. So perfect matching is a matching. And what sort of matching is it? Matching such that each vertex is covered. Each vertex covered means if you have edges here, then you collect edges here, right? V1, V2, V5, and all. So each vertex should be present here. That's what your perfect matching is. So it should be a matching, and each vertex should be present in the matching. That's when you say
In
that
the
matching.
in the
Yeah. So in
earlier
this
example,
example,
we have taken V2, V3, V4, V5, but we haven't taken V1 and V6. So
yeah,
it is not an example of perfect matching, right?
this is not a perfect matching. Then this one, what about this one?
It is a perfect matching because we have it contains all the elements, all the vertices.
We've collected all vertices here. We've ensured that every vertex is here. That's why it's a perfect matching. Is that okay? One example of it could be, let's say you're doing a group project, or let's say you're doing a project where only two people are supposed to, either you're allowed to do the project alone, or you're allowed to group or make pairs and then do the project in pairs. So let's say these are people here, V1, V2, V3, V4, and V5. Or let's take the previous one only. If we take this example, let's say these are people, and then let's say, and these edges here, so these are people that are supposed to do the project, and this, let's say, is the this edge represents friendship here, let's say. So if these, like, if you have an edge here, then these two people are friends, that means. And we are saying that only the people that are friends are going to pair for the project. The people that are not friends are not going to pair for the project. That's an assumption here that we're making. So now if you need to find the matching, because you can only have either two people or a person working alone for the project, right? So this is a matching. That means these two people will work together, these two people will work together, and then V1 and V6 will be left alone, do the project alone. And this is a perfect matching where everyone has a partner to the project with.
Ma'am, it will not work when there's a odd number of vertices, right?
Yeah, when you have odd numbers, now it automatically tells us this thing that if you have odd number of vertices, if you have V1, and then you, instead of V6, let's just remove one from here only. So if I remove this vertex here, so matching would still work. If I remove this vertex here, V6, then I can have V1, V2, I can have V3, V4, but V5 is left alone. So if you have odd number of
So,
vertices, then obviously one person will be left alone.
and
So
then
you
it
can
won't
have a
be a
matching.
perfect matching.
What?
Perfect matching possible then.
Yeah, perfect
Okay.
matching is not possible. Matching is still possible.
Okay.
Is this
So, ma'am,
entire
you are
matching
saying
perfect?
perfect matching only happens when we have even number of vertices, na?
Yeah, perfect matching, because you have to, what you're literally doing is you're clubbing the vertices into pairs. So if you want to make pairs, you obviously need even number of vertices to ensure that every vertex is included in one pair and only one pair. Okay, can we move on to the next topic?
Yeah, ma'am.
Yes, ma'am.
Okay. And from here, the next thing, important thing is adjacency matrices. So when you have a graph, and we discussed two types of graphs, right? One is the directed one is, and the other one is undirected. Let's just talk about the undirected first. So when you're talking about undirected graphs, adjacency matrices are basically, let's say you have vertices V1 to V5 or to V4. Then to draw an adjacent or to make an adjacency matrix, first you write all the vertices here in column and then in rows here. V2, V3, or you can do it like this. V1, V2, V3, V4, V5. And we'll write one here. So the one with the same things, V1 to V2. So this is V1, V2. We'll put a 0 there. V2 to V2, we'll put a 0. So on the entire diagonal, we'll have 0, right?
We have only till V1 to V4.
Let's have it from till V5 then. And then if there is an edge between V1 and V2, you write a 1. So on the diagonal, you just write 0. Because we don't talk about V1 to V1, right? When we were looking at graphs, we didn't have a concept of an edge between V1 and V1 or the same vertices, right? So there we are writing a 0. And wherever we have a vertex, so if we have a vertex from V1 to V2, we write a 1, else we write a 0. So if there is, let's say you have a graph V1, V2, V3, V4, and V5, and it's this, then we know that from V1 to V2 there is an edge, so you should write 1. From V1 to V3 there's no edge, so you should write 0. From V1 to V4 there's an edge, you should write 1. And from V1 to V5 there's again no edge, so you should write 0. The same way you fill this entire table, this entire matrix actually. This is a matrix, right? That's called your adjacency matrix. Is that okay?
Yeah.
Yes,
And this is
ma'am.
in case of undirected graphs. So in undirected graphs, if I have an edge from V1 to V2, because there's no direction, we don't say that there's an edge from V1 to V2. Now, when I do this thing, I mean, if you have this graph, you mean you have an edge from V1 to V2, but you don't have an edge from V2 to V1. Like, let's say there's a one-way path to go from this place to this place, but you don't have a path to return from this place to this place. That means this is a directed edge now. So this one's a directed case, this one's an undirected case. In an undirected one, you mean you can go from V1 to V2 and V2 to V1. So when there are no directions, we automatically mean that it's directed in both ways. Like in friendships, it's directed in both ways. V1 is a friend of V2, V2 is a friend of V1, right? So if you have an edge from V1 to V2, you should have an edge from V2 to V1 too, right? So we'll have a 1 here. So if these two entities, that means if this is a matrix A, and Aij, I hope you're familiar with this notation. Aij means Aijth entry, where I is the row number and j is the column number. These are rows. These are rows, first row, second row, third row, and so on. And these are columns. And Aij, when I say, so this is ith row and jth column. So if I say A23, then it's second row and third column. This is second row, this is third column. So it's this entry.
Ma'am,
If
friends
you
are
have
brothers are same. Like if you are saying V2 is the brother of V1, so it's same as brother.
So if you say, if you are including both genders and you've not mentioned that they're all males, then if V1 is a brother of V2, then you can't say V2 is also a brother of V1, right? It could be a female. And in that case, it's not, she can't be a brother. But if you mention that they're males, then obviously V1 is a brother of V2, then it would be an undirected graph. You can just use this arrow. If this is a brother of this person, then obviously this person is also a brother of this.
Ma'am, but if it is a directed graph, we can say that B is a brother of A.
Yeah, you will be given that. If I say in graphs and in every problem, if you're given this arrow, you would be specified what this arrow means. They'll tell you if A is a brother of B or B is a brother of A. They'll give you all this. Don't worry.
So ma'am, adjacency matrix means it will be a diagonally flipped mirror image, right?
Yeah,
That's
diagonally
why.
flipped mirror image, and that's called a symmetric matrix.
Okay, symmetric matrix.
We
Only
were
in the
talking about that only.
undirected ones.
Yeah, and that's for undirected ones because yeah, we'll come to that. So if you have Aij, and this is for undirected ones, we're talking about undirected graph. So if you have Aij, that means there's
AJI
an
will
edge
be
from
same.
Vi to Vj, right? There's an edge from Vi to Vj. And because it's an undirected graph, that means there's an edge from Vj to Vi2. Because it's undirected, that means your Aij and Aji should be equal to 1. So either they're both 1 or they're both 0, right?
Okay.
Like in this one, if you have an edge from V1 to V2, then you also have an edge from V2 to V1. So in this one, A12 and A21 entries both will be equal to 1. And A13 and A31 entries both will be 0, right?
And the
Okay.
last concept, can you repeat that AIG is equal to AJI is equal to 1 and 0? What was that?
Okay, have a look at this graph. When you have this graph, I say A12 is equals to 1. What does that mean? A12 is this entry. This one, this is A1 and this is 2. So this entry, this is 1. What does this mean? That there's an edge between from V1 to V2, right? That's when we write a 1 here. But if you have an edge here from V1 to V2, that means you also have an edge from V2 to V1, right? Because it's an undirected graph. That means if your A12 is 1, which is true because you have an edge from V1 to V2, that means your A21 is also 1 because there'll also be an edge from V2 to V1. And if your A12, A13 is 0, yeah, A1 for this graph, A13 is going to be 0 because there's no edge between from V1 to V3. So A31 is also 0, right?
That is for undirected graph only. Okay.
Yeah, that's for undirected graphs because there are no directions here. V1, V2,
Uh,
V2, V1 mean the same thing.
so, ma'am, can you take an example of directed graph? How we'll take that adjacent matrix on the directed graph?
Do that. And so here what we mean is if A13 is A13 and A31 are same, and A23, A32 are also same. That's what we mean here. When I write 1, I mean either they're both 1 or they're both 0. That's what I mean. That's called a symmetric matrix. When you have Aij equals to Aji, that's called a symmetric matrix. This is the matrix and these are entries.
But this is only in the case of undirected graph, na?
Undirected graph. And in the case of directed graph, let's say you have V1, then you have V2. Let's take the simple one only. Now if I'll do V1, V2, V3 here, and V1, V2, V3 here, then here I'll have a 0 on diagonal. And from V1 to V2 you have an edge, you should put 1 here. From V2 to V3 from V1 to V3 you should put 0. But if you look at from V2 to V1, now you don't have an edge from V2 to V1, so there should be a 0. But in the case of an undirected graph, there should have been a 1 here, right? So in this one, and if it was both ways, if it were like this, then you do 1 here. Then we'll have a 1 here, right? And from V2 to V3, there's again 1. V3 to V2, no edge, so you should have a 0 here. And what's left, V3 to V1 is also 0. Is this okay? So if you
And
look at this,
diagonal should be always zeros, right?
yeah, it's always 0 because V1 and V1 to V1, we don't consider any edge. That's why.
Ma'am, you are considering row and then column, right?
Yeah.
Okay, ma'am.
Ma'am, can we say that
In a
symmetric matrix is
directed
always a
graph,
case of, ma'am, can we
one
say that
second,
symmetric matrix is always the case of undirectional graph, but not in directional graph? We can say that symmetric matrix is there.
one second. When you have this thing, And this one, when in undirected, it doesn't matter if it's from V1. When you write it in this manner, and when you say V1 to V2, when you put a 1 here, it means you have an edge from V1 to V2, starting from V1 and directed towards V2. That's what we mean. So this one represents an edge from V1 to V2, this edge, and this one represents V2 to V1. So here outgoing and here incoming. Is that okay? The edge goes from
Yes,
here
ma'am.
and
Okay.
comes here.
And as we
Yeah.
are dealing
Yes,
with
madam.
the matrices, we always consider being a key and then values. It will be like row first considered and then columns, right?
What?
When we in this case of matrices and all,
Yeah.
always consider the row first and then the columns because it's like a key value pair dictionary, right?
Yeah. It's if you write it in this manner, then the first entry is the row one, and this is the column one. You consider rows first and columns later.
And I'm started
Okay.
from the upper left corner, row 1 and column 1.
Yeah, this one.
The
Start
upper
from here.
left corner start from.
Okay.
Ma'am, I was
So yeah,
saying that the symmetric matrix is only the case of undirected graph and the both
yeah. One
directional graph,
second, I'll
na?
explain that thing. When you have an undirected graph, if you have, then obviously the matrix that you're going to have is symmetric matrix you'll have. But if you'll have a directed graph, then you can't say. It can be a symmetric matrix or it can't be a symmetric matrix, depends on the graph, right? Can't say. So it can be symmetric, can't be symmetric. So you can't say if you have a symmetric matrix, then it's definitely an undirected graph. Is that okay?
And for the both directional graph also, we can say that it's symmetric matrix in a way.
Yes.
Post directional, both directional.
The graph which, the edge which is going both the side, V1 and V2 both.
Yeah, if it's going from V1 to, now that's if your entire graph is like that. If you say that if your entire graph is this only, then it's an undirected graph. It would be treated like an undirected graph only, right? Because when I discussed undirected graph, I discussed this thing. This edge means that it's directed towards this thing too and directed towards this thing too. So it goes both ways. In an undirected graph, it means the direction is both ways.
Okay, ma'am.
So if you have a graph in which every edge is either both ways or there's no edge, then it's an undirected graph only, right? I mean, by definition, it's directed if there are arrows, but it can be treated as an undirected graph, right?
Yes, ma'am. Okay.
Okay. Then we have degrees of vertices. So degrees of vertices, let's say you have degree V1. Degree means the number of edges connected to. So if you have an undirected graph like this one, so degree of a vertex means the number of edges that are connected to this vertex. So here V2, the degree of V2 should be 2 because there are two edges that are directly associated to V2, right? Right. And then the degree of V1 should be 2. Degree of V2 should again be 2. Degree of V4 should be 2. Degree of V5 and V3 is 1. And if you'll make the graph like this, then the degree of V1 is 3. 1, 2, 3. Is that okay? So in an undirected graph, that's the concept of degree. Degree of a vertex is basically how many edges are connected to that, how many edges are uh, on that vertex. Is that okay? That's your degree of vertex. It's used when
Um,
you're undirected graphs.
got it, ma'am.
And then we have in degree and out degree. In degree of a vertex and out degree of a vertex. In degree means the number of incoming edges to that vertex, and out degree means the number of outgoing edges. Like if you have this thing, V1, then the in degree is the number of incoming edges. So it's 1, 2, and 3. In degree is 3. And the number of outgoing edges is only one outgoing edge, this one, so it's 1.
This in degree and out degree is only possible for directed uh, vertices, right?
Graphs. If you have directed graphs, then obviously all the edges are directed. It's for directed graphs, and this one is for undirected graphs. And reachability, we've already discussed what reachability means. Reachability means if I say that V1, V5 is reachable from V1, that means there's a path from V1 to V5. Or you can reach from V1 to V5. And you can check the reachability using the matrix too. So if you have a matrix, let's just fill this matrix. So if you have a 1 here, V3 and V1, so this should be 0. And then V1, V3, V1, V4 is 1. This should be 1. And this should be 0. And then we can just do this thing. This is, let's take 1 here. Randomly filling these things, not using this graph. V3, V2, and then V2, V3 should be same. So 1 here. And then for this one, V2, V4, let's take 0 here, 0 here. And then V3, what's left? This one, V2, V5, let's take 1, 1. Or let's just do, because let's take the case of undirected only, then we'll not have to worry about these
Ma'am,
things.
in V3, V1, it should be 1, na?
We're doing it as per directed graph. Let's consider this to be a directed graph. Because undirected graphs, it's taking time. So we're directly doing this thing. Let's take a random adjacency matrix of a directed graph. This is for a directed graph, obviously. Then discuss the reachability, because we know it's a little difficult to check the reachability from here. If you have to check the reachability, let's say you have to check if V3, V5 is reachable from V3. So you will first go to V3 and check if there's a direct edge between V3 and V5. If there's no direct edge from V3 to V5, because we have a 0 here. Then you go to V3, then you check where there is a 1. So there is 1 here. There's no point going to the 0, right? I hope you understand why there's no, what we're trying to find out reachability from V3 to V5, where we know that there's no direct edge from here to here. So now we're trying to find the path. Can we have V3, V4, V1, and then V5? Can we have something like this? So we're trying to fill in these gaps here.
Just,
So if you
ma'am,
have 0 here, you shouldn't be considering V1 here, right? Because there's no edge from V1 to V3 to V1. So you should be considering these ones. So you can consider V2 here. And then if you'll go to V2 here. So from V3 to V2, and then you go to V2, and then you see you can go to V1 too, right? You can go to V1, and you can go to V3. But V3, we've come from V3 only, so we don't want to go to V3. You can go to V1. If you go to V1,
Ma'am, but V2 is also going to V5, like there is one.
yeah, it's directly going to V5, right? So you can just directly take 1 here. This, then you can have V3 to V2 to V5, or you could have another way too. So let's just find the shortest only. That's easier. That means there's a way from V3 to, there's a path from V3 to V5. So you can figure out using this matrix too. Right? Adjacency matrix helps you figure out the reachability. Graph does
And
too,
how is
obviously.
V1 to V5?
Is there a doubt?
Ma'am, how is V2 connected to V5 in the previous example which you told?
This one?
Yes,
We
ma'am, I
have,
have a doubt in undirected graph.
there's one.
Because
That V2,
in the graph it's not connected.
I already mentioned that I have not used this and I have not written this matrix as per this graph. This is a random matrix I've taken. Initially, I was trying to do it as per this graph, but then I dropped the idea. This matrix is not connected to this graph. This is a random matrix of some other graph. Is that okay?
Yes, ma'am.
Yes, ma'am.
And then there's something called adjacency list. So in adjacency list, it's basically the collection of all these. So we make it like this: V1, V2, and V. Let's consider this graph. So you write all the vertices that are reachable from, not reachable actually, that are directly connected to V1. So in this one, you write the vertices that are directly connected to V1. So if you look at this graph, the directly connected ones are, we should be writing just V3, right? V3 here, because only V3 you can reach from here, right? And then this ends here. For V2, you can reach you can go to V1 directly, and that's it. That should be it. For V3, you can only go to V4. That should be it. And then for V1, it's like the collection of all the vertices that you can directly go to. Directly go to in the sense not via path, but via an edge.
Ma'am, what does it call? Adjacency list.
Adjacency list.
Okay.
So what you're doing here is, if there is an edge, simply you're collecting the elements that have edge. So in an undirected graph, there's no problem because there's no direction. But here you have to be a little careful. If you write V3 here, that means V1 to V3, there's an edge. That's why you write V3 here. So all the points that you can go to directly from V1 are here in this adjacency list. So
Ma'am,
this entire thing is called adjacency.
if we take V4 here, so V4 is going to V1. You can also write this or not?
Yeah, V4 you can write V1 here.
Okay, got it.
You have to write all the vertices here. V5,
No,
V4.
I just, yeah.
That entire collection is what you call adjacency list. Okay. Then we have the number of edges in a graph. So let's say you have an undirected, just quickly go through this thing. If you have an undirected graph, let's first take the undirected graph. Let's say you have this thing. You have, let's say, n number of vertices. Then how many maximum edges are possible in an undirected graph? An undirected graph with n vertices, how many maximum edges are possible?
N
N,
minus 1.
N minus 1
N
upon 2.
N
minus
minus
1.
1. N minus 1.
N minus 1 upon 2.
It's n minus 1 upon 2. And how do you get this n minus 1 upon 2? It's, if you have, let's say, this first vertex you take, I know that I can just, the number of edges I can have from here is 1, 2. So I can have only 2 edges, right? If there are n number of vertices, there are 3, so I can have 2. If there were n number of vertices and you start from one vertex, then the number of edges starting from this vertex and ending at some other vertex, maximum number of edges is n minus 1, right? And then you take the second one, that will be n minus 2. And then you keep adding like this, and you stop at 1. So the sum is actually n minus 1 by 2. That's why there are n minus 1 by 2 number of edges, maximum number of edges in an undirected graph, n vertices. If you have an undirected graph, n number of vertices, the maximum number of edges is this. Maximum number of edges. Obviously, there could be edges less than this. And for a directed graph, it is n minus 1 by 2 into 2 times, because you can have it in both directions, right? That's why you should have n minus
Your
1
voice is
number
a
of edges.
little bit breaking.
Yes, ma'am. Your
Better now?
voice is little crack. I mean, too late. Yes, ma'am. Now it's okay.
Okay. So this is for undirected graph, and this is for a directed graph. So if you have
Ma'am,
a
your
directed
voice is
graph,
little bit breaking, ma'am. Ma'am, your voice is little bit breaking.
Yes, ma'am. Your voice is lagging behind like that.
okay, just 1 second then. Is it better now? Is it still breaking or lagging?
No, ma'am. Now it seems
Better now.
fine.
Okay.
Ma'am, there is
So
one doubt. When you add n minus 1, n minus 2 to till 1, how the formula came, n minus 1 upon 2?
okay, the sum the sum of first n natural numbers is n plus 1 by 2. That's the sum of first n natural numbers, and these are first n minus 1 natural numbers, right? So instead of n, you should have n minus 1, and here you will have n minus 1, so you'll end up with n by 2. Is that okay? This is the formula for the sum of first n natural numbers, which comes using the AP formula, arithmetic progression.
Yes, ma'am, got it.
Okay.
And
So
ma'am, the last two, yeah, that is for the
this is
undirectional graph, and for the n minus 1, how
this is for directed graph, because if you have this thing, so here till here you have taken these things, right? If you have 3, you have taken these edges. But what do you do in a directed graph? You take both directions, right? That would be the maximum number of edges. So this edge in undirected graph you were considering 1, but in a directed graph you're considering them to be 2, right? If this is an edge in an undirected graph, this is considered 1. But in an undirected graph, the maximum number of edges you can have for 2 vertices is 2, right? From here to here
Yes,
and
ma'am.
here to here. That's why we're multiplying this entire thing with 2. So
Just one thing, ma'am, this E in the bracket, what it is called, the definition, like this E in the, yeah,
which one?
the E in
This
the matrix, what it is called, the name of that
this
is
thing.
edges.
This
Cardinality.
is cardinality of set E. We discussed
Okay,
this
ma'am.
in the starting, right? This is the collection of
Yeah,
all the
ma'am.
edges.
Yeah, ma'am.
This is
Okay.
a set, and this is the cardinality of that set. Okay. So then coming to the next
Ma'am,
topic, which is
this equation will only work if everything is connected to everything, right? Like,
yeah. That's why we say the maximum number of edges.
okay,
Maximum number of edges. This is.
okay.
Then we have something called, now we were discussing reachability, right? And we said that we can use matrices for it. But it's not you can also use adjacency lists. But those are not very feasible options. Like it's a very tricky thing, long thing. So we need something simpler to discuss reachability of vertices from some vertex, right? So let's say you have a graph. So there are two approaches to it. There are two methods to do this thing. To discuss reachability. One is BFS approach and the other one is DFS approach. So this is breadth first approach and this is depth first approach. One second. Yeah, so this is depth first and breadth first, right? So let's start with the BFS approach first. Why are we using these approaches? This is to discuss the reachability of the vertices from one vertex, or it could be any vertex. So let's say you have a graph V1, V2, V3, V5, V6, V. Let's say you have this thing. Say you have this graph. And in this graph, first, so let's just start with this vertex only. Let's see what vertices can we reach from first vertex. Let's consider this vertex. We are trying to find all the vertices that we can reach from this vertex. And for that, we're doing the breadth first search. For the breadth first search, uh, first you start from V1, right? So we consider Q first. This is called a Q, where we collect vertices. And in what way do we collect vertices? We start from V1 and then we see all the directly reachable. When I say directly reachable, I mean the vertices that have a direct edge with V1. So we put V2 here, V3 here, because they have a direct edge with V1. Right?
Ma'am, is
Put
it a
these,
queue or a stack?
this is the queue. For the BFS search, we're discussing BFS first. So that's a queue. In DFS, what we use is a stack. We use a queue. So we start with V1 only. Actually, we have started our search from V1. So we write V1 first. Then we see all the vertices that are directly connected, that have a direct edge with V1. So that's V2 and V3. We write all those vertices. If you have V6 too, then write V6 too. Write all of them. And then you start from this one. Now this has been explored, right? Okay, we'll be using two terms here, new terms. So first is visit. The other term will be explore. So visit means visiting this vertex. As in you go from this vertex to this vertex, then you say that this has been visited. Like in this example, you started with V1, you visited V2, V3, and V6 because they have a direct edge. So we say V2, V3, V6 have been visited. But explored means when you say that this vertex has been explored, we mean that all the vertices that were directly connected to this vertex are have been visited. So if V2, V3, V6, because they have been visited, because they've mentioned them here, that means V1 is explored. That means we're done exploring V1. Exploring means going to all the vertices that are directly connected to this. So exploring this vertex means going to all the vertices that are directly connected to this vertex, or visiting all the vertices that are directly connected to this vertex. And when we're done doing that, we say that this vertex is explored. So because we've mentioned V2, V3, V6 here, that means we've visited these vertices. That means this vertex has been explored, right? We can just, and the one that are done exploring, they are removed
Your
from here.
voice is a little bit breaking, ma'am.
Can't do anything about it. Is it still breaking? Is it okay now?
No, ma'am, your voice is clear.
Okay.
Breaking intermittently, ma'am. Sometimes clear, sometimes it's good.
Okay. So
Then we include V1 in the table, right?
yeah,
Okay.
you include V1 here in this queue. Then you visit all the vertices. Visiting means just going there. It's consider these to be places, right? So this is a place, and then from this place you can go to this one, this one, this one. And when you
Okay,
have
ma'am.
visited all these places, then you say V1 has been explored. We're done exploring.
Ma'am,
Okay, ma'am.
you have drawn the 9 boxes, but the vertices is only 7. So
That
is it
doesn't matter.
related with
We can extend the queue from here.
it? Okay.
I was just trying to explain this idea of BFS approach to you. So V1, you start with V1, then you write V2, V3, V6. That means, and that's why it's called breadth first search, because you're going into breadth first. You're covering the entire vertices that you can go to from here. So V2 is covered, V3 is covered, V6 is covered. If there are other vertices directly connected to this, then write them here. And then this is explored, right? So you cross this thing and you do, and we make a tree simultaneously. Let's take the tree too. Let's make the BFS tree simultaneously. We'll come to how to make a BFS tree. Okay, we have not discussed tree yet. So we'll come to that one later. Let's just discuss the approach first. So your V1's done. Then you go to V2 and you start here. So your idea in BFS is first in, first out. That means the vertex that comes to this queue first will leave this queue first. This one, V1 came first, so it will leave first because we're done exploring this. So we'll remove this from here. Then we come to V2 and we see V2 is directly connected to V5 and V3. But V3 is already in the queue, so you don't have to write it again. Write V5 here. And no other vertices, right? So we're done here. And then V2 is also explored because all the vertices that were directly connected to V2 have been visited. That's why V2 has been explored, right? So you can remove V2 from here. And next up, you go to V3. So notice that V1 entered first and then it left first. So the next one in the line was V2, then it left. And now it's V3's turn. So you come to V3 and then see what are directly connected to it. So V6 only is directly connected to it, which has already been written in the queue, so you don't have to write it again. That means V3 is also explored,
No,
right?
that V6 is different from the other one. Either remove it or there is a
No, no,
V6 connected to V1 and there is a V6 connected to V3 directly.
we've written V6 two times.
Yeah,
Let's take
2
V7.
times. V7 is already there in V5.
Ma'am,
Make it
V4
V4.
is not.
V4 is not there.
V4 is not.
V4 is not there.
No, ma'am.
This is it. We were on V3, right? So V3 is connected to V6. It's already in the queue, so you don't have to write it again. This is also explored. Then you come to V6. V6 is this one. And V6 is directly connected to V3, already visited.
Madam, it's a
Then
bit confusing because
V3,
we
That's
made
V4.
V4 right.
That's V4, man.
V6 should be V4 in your queue.
In the queue, V6 should be V4
Yes,
okay,
ma'am.
because
okay,
V4
okay.
is directly connected to V1.
Thank you.
Yes, it should be V4.
Let's just start the queue again then.
Yeah.
This is it. You start with V1, and then the directly connected ones are V2, V3, V4. You can write them in any order, doesn't matter. V2, V3, V4. But when you have written V2 first, now you should start with V2 only. So this has been explored. Coming to V2, V2 is directly connected to V5, right? V5 here, and it's directly connected to V3. V3 is already in the queue. Need to write it again. V2 is also explored. Coming to V3, V3 is directly connected to V6. You can write V6 here, and that's it. That means V3 is also explored. Let's remove this from the queue. Then you have V4. V4 has only one vertex connected to it directly, which is V1. You don't have to write it again. That's also explored. Coming to V5, V5 has V6 and V2, and both of them have already been explored. So you can remove
V7.
that too.
V5 to
V7 is also
V7.
there. V7 is also there, right? V7. Then this is explored. And coming to V6, I think all of them have been written, right? V1, V2, V3, V4. And in the right, in the ascending order only of their indices. So all the vertices has been visited. That means from V1 you can visit every other vertex, right? From V1 you can visit V2, V3, V4, V5, V6, V7. That means every other vertex is can be visited from V1. But let's put directions there and then see what happens. I'll put directions here.
Shouldn't we put cancel on V6 and V7 also? Because it has been explored also. Like trick mark
Yeah,
on.
you can cancel them. Everything has been explored.
Madam, what are we trying to find with this, let's say, by making queue and exploring and visiting? Like, what is the final objective?
Our objective is to find the reachability from one vertex to other vertex. So let's say
Ma'am,
you
but
start
I
with
have one
V1.
question.
1 second, let me just answer this thing. So you start with V1, you just check all the vertices that have been mentioned there. Like, let's say you had it'll be more clear when we'll do it in a directed graph. Then you will be able to see which vertices can be visited from V1. When we say every vertex has been there in the queue, that means you can
Mhm.
visit every vertex from V1 because every vertex has been covered in the queue. But
Okay,
when we
yes.
do this directed graph, then there can be vertices that you can't visit from V1, right?
So we can make queue for, let's say, if I want to make a queue for V5, then I should write V5 in the first column, right?
Yeah. First,
Oh,
then you will start with V5.
okay. Okay,
Let's
thank you.
do it from V5 only then. If you start from V5, your queue starts from here. And the arrows are you have arrows V7 to V7, you have an arrow. And then that's it, right? Okay, that means you can't visit any other vertex except V7. So the search is like, this was a very short search. Let's try from
Ma'am,
some other
but
vertex.
the queue is
From
quite
Ma'am,
unclear
V7 is
because
also going to V3, right?
no, this graph's not clear. This is V7 and V7 is only this. That's it. V7 is not going to V3.
ma'am, you have also written V4, V5, but V4 and V5 are not at all connected. In the queue, you have written V4, V5, but V4,
Okay, in
V5
the
are
queue, I've
not
written
connected.
we don't write, when we do that, let's just forget the arrows here. That was our undirected graph, and this queue was for that undirected graph. And
Okay,
when you
ma'am.
write V4, V5, because they're written next to each other, doesn't mean you can go from V4 to V5.
Okay, ma'am.
It's
That's
just the way you
understood.
use the breadth first search. Right, all the vertices that you can visit from the first vertex V1, let's say you're starting from V1. So all the vertices that you can visit from V1, then you start with the second one, this one, and all the vertices that you can visit from V2, write them. And all the vertices you can visit from V3, write them. That's how you do the breadth first search. If you start for this undirected graph, let's say if you start from V1, you'll have, so you can go to, from here you can go to V2, that's it, right? So V2 is only there. And then from V2, this is explode, right? Because you can only go to one vertex, V1. You can't go to V3, can't go to V4, and other vertex also you can't go. That means only V2 is there for this one. That means this is explode. Coming to V2, you have V5. This, let's take it this one. That means you can go to V3. You can go to V3 and V5. So we've written V5 and V3. You can change the order too. Doesn't matter. And V2 is explode, right? So you can cross this one. And you have V5. From V5, you can go to V7. And that's it. V5 is also explode. Then coming to V3, you can't go anywhere from V3, right? That's also explode. Then you have V7. V7 also you can't go anywhere. That's also explode. That means from V1, the only reachable vertices are V2, V5, V3, and V7. That's it. Now all the ones that are left, V6 is left, V4 is also left. That means these vertices you can't reach from V1. That's your breadth first search. And you can start from the vertex that you need to find uh, the reachability from. So if you have to find the reachability from V1, start with V1. If you want to find the reachability from V6, start with V6. Is that okay?
Yes, ma'am.
This was just the idea for breadth first
Yes,
search.
ma'am.
How you do the breadth first search.
Second queue, you did the BFS for directed graph.
Yeah, this one's for directed.
So in this, we can't reach V4 from V1, right?
Yeah. Only these vertices you can reach.
With respect to V1.
Yeah, reachable from V1. Start from the vertex that you need to find the reachability from. So if you need to find the reachability from V1, start from V1. And let's do the depth first then. So let's do it for this one only. So in the depth first search, what you do is, in this one, what we were doing was we started with V1 and then so let's do depth first for the undirected one. So let's forget the directions in this graph and do it for that one. DFS search. So what do you do in a DFS search? So now here this thing is called a stack. You maintain a stack here. What do you do in this stack? You're starting with V1, right? So V1 is the first one. Then you write the first vertex or any vertex that you can reach from V1. No, note that we're not considering the directions here. We are doing the depth first search for undirected graph first. Then we'll come to the directed one later. We start with V1 and then we write, you can write V2, V3 and V4, right? But that was for depth first search. You just write one vertex here. Choose any one from these three and write it here. Let's just choose V2. So we chose V2 and then you start searching from V2. So now you we say that V2 has been visited, right? Just 1 second. Start from V1, then you do V2. Instead of writing all the vertices that are directly connected to V1, you write just one vertex and you start exploring that vertex instead of completing the exploration of this vertex first. So in breadth first search, you start with V1 and you explore every vertex, you visit every vertex connected to this. That is V4, V2, and V3. And then you get done with the exploration of V1. But you don't do that here in DFS. You start with V1, go to V2, and instead of doing all these, you continue in V2 only in this direction. So then you start exploring V2. So coming to V2, you can go to V5, go to V3, and that's it. You can write V5. So let's just pick one of these, V5 and V3. Let's choose V5. Then from V5, you can go to V6, write V6, or you could have written V7 too, doesn't matter. And from V6, you can go to V3, right? And then V3, you will come back to, so after V3, now when you reach to V3, there's no new vertex to visit, right? When you reach V3, first you start from V1, going into depth, you reach V2, then depth V5, then depth V6, V3, and then V1 is already been visited. That means you don't have to write it again in this stack. Then you start tracing back from V3. And this is first in, last out. That means the entry that enters first, the vertex that enters first, leaves last. So you have V1 here, right? So, and the last one exits first. So this is the last one. So this will exit. And you are anyway done exploring everything, right? You go from this to this, then this, then this, then this. You're following the depth. And then after V3, you don't have anything to visit. That means we're done with V3. You can remove this thing. And then you go back to the previous one. That is V6. That's why we have this stack here. Go to V6. Now there's no other vertex to, let's say if you had a V8 here, right? Then you would write a V8 here. So what we're doing here is V1, choose one vertex that is directly connected to V1. Let's choose V2. Then we went to V5. Then similar way V6. Then we could have chosen V3 and V8. So we chose V3. And then after V3, there is no new vertex to visit. So we start tracing back. From V3, we go back to V6. But V6 is not yet explored because V8 is left, right? We say a vertex is explored if every vertex directly connected to it has been visited. V8 has not been visited yet. So you write V8. Now we can say that V6 has been explored, right? So you can cancel that then. Then from
V4 also not visited. Then
yeah, it's not visited. That's why we didn't say that V1 has been explored. V1 is still to be explored. We're not done exploring V1. The one that I put cross to are the ones that we're done exploring. So V3, we're done exploring. V6, we're done exploring. Because all the vertices that are directly connected to V6 has been visited. So we're done exploring that. And then you have, after V8,
we also
you have,
like done with V8.
Yeah, you're also done with V8 because there is nothing to explore. You say you're done exploring with the vertex. Every vertex connected to that vertex has been written here. So V8 is not connected to any other vertex other than V6, which is already in this stack. That means V8 is also explored. And then you will trace back, right? From V8, you trace back to V6. V6 has been explored. You trace back to V5. In this, look at this stack. V5 is the last one. You trace back to V5. V5 has V5 has V7, right?
Yeah.
You should write V7 here.
So, ma'am,
Then you see,
when we are tracing, we have to go backward in a way from the graph.
yeah, from here you have to go back and you can check it here. Like the last one you have to visit. Now the last one is V7, right? So you should trace back from V7. V7 to V5 you will trace back here, right? Because you came to V7 from V5 only. That's why you trace back to V5. You're done exploring this. Then you come back to V5. V5 has no other vertex directly connected to it. So you're done exploring V5. Then you come back to V2 here. V2. Then V2 has V3, right? V3 has already been covered here. So this also you are done exploring. So this is also done. And then you come back to V1. That's also done. Now from V1 you have V4, right? So you write V4 here. Now if you have anything connected to V4, you write it here next to this. But since V4 has no other edge, that means you're also done exploring V4. And then because every vertex directly connected to V1 has been written here, that means V1 is also done.
So, ma'am, these two method, DFS and BFS, the only mission of us is to know the reachability, na? That's all.
Yeah, it's about the reachability. And then later on, we'll see other applications of BFS, DFS too. But for now, it's just reachability. And
In the case of DFS, ma'am, the reachability of V1 we had discovered, is it right or not?
yeah, this is for reachability of V1, this entire thing. So all the vertices that are there in the stack are reachable from V1 for an undirected graph. Now, if you will do it for the same for a directed graph, the things will change here. Should I do for the directed one too? You start with V1, then you can go to V2. Following this, you can go to V5. You can also go to V3. Let's go to V3. You can go to V3, and then from V3, you can go to V1. That means, and it's already in this stack, that means you're done exploring V3. And then you come back to V2, this one. Then from V2, you go to V5. From V2, you go to V5. And then from V5, you go to V7, let's say. V7, you have no other vertex to visit. That means you're done exploring V7. Come back to V5. Then no other vertex from V5, no other outgoing edge. That means you're also done exploring V5. Then come back to V2. No other outgoing edge. That means V2 is also done. Come back to V1. No other outgoing edge. That means V1 is also done. That means it's V1, V2, V3, V5, and V7.
So,
Right?
madam, answer
And
is same only
notice
whether
that
we
we got the
follow
same thing.
BF or DFS. The answer is
Yeah.
going to be same.
Yes. These are just two different approaches. Answer, this is the same as this one.
Ma'am, at the end, we have to cancel everybody. In a way, we have to explode everybody. So that is the
Yeah.
complete thing, na?
Yep. But they follow different approaches. So when doing a BFS, you do this thing V1, and then you explore every possibility here, V2, V5, V6, and then you start from here. Then you start exploring this one, write these here. Start exploring this one, then write these one here. Then start exploring this one, then this, and then go to this one. I hope you understand what I'm saying. So this is called level 0. This is level 1. This is level 2. This is level 3. So get done with the first level, the 0th level, then first level, then second level. Don't jump onto the third one. But in a
What is
depth
the
first
need of
search,
two different approach for the same problem? Like, what is the need?
we'll do this when we'll do the DFS and BFS. This is just a basic idea of what BFS and DFS search is. There's way more to it that we have not done yet. Should I cover that?
Ma'am, what was the last thing you said? It's like
Yeah, your voice is lagging, so we are unable to hear that.
just last
I wasn't
sentence.
saying
It cracked, na?
anything
Yeah.
towards the end. We're just saying that there's more to the DFS and BFS thing, and we'll come to that later. This is just a basic idea of what DFS and BFS looks like. So if you start with this thing, we can do this thing right now. Let's say you have A, then you have B, C, D here, and then E. This is called, now when you do this thing, we can make, let's do BFS and DFS tree first. So in a BFS tree, how do you draw a BFS tree? Let's start with this one only. Let's draw the BFS tree for this one. So we're starting the search from B1. Then we go to V2. We're doing it for the
You're
directed
not
one.
audible.
I'm not audible at all, or
No, ma'am,
is
you're
my
audible
voice
now.
breaking?
No,
Okay.
ma'am, you are audible.
Ma'am,
Now
you're
you are
audible.
audible,
Okay,
ma'am.
madam, you're audible.
Ma'am, just can you repeat what are you doing right now? What have you
We're
started?
making a BFS tree. BFS tree is a thing. We're making a BFS tree for this entire thing. Or let's do the BFS tree thing later because we're not left with a lot of time. Let's just discuss some basic definitions before this. So there are some the definitions. First one is the connected graph. So what's a connected graph? And connected graph is used when you are talking about undirected graphs. So this is the terminology used for undirected graphs. And for directed graphs, you have strongly connected or weakly connected. This terminology is used. Strongly connected and weakly connected or directed graphs. So what do these things mean actually? So this first one, connected graph means where every vertex is reachable from every other vertex. So let's say you have V1 and V2. Now if you have this thing and you have V4, V5 and V6 here. So do you think this is a connected graph? The definition for a connected graph is you
No,
can
ma'am.
reach
No,
every
madam.
vertex from every other
No,
vertex.
it is not a connected
This
graph.
is not connected, right? And this is an undirected graph, so you call it a disconnected graph. In terms of when you're talking about undirected one. Now let's just use arrows here. And okay, before arrows, let's just do this thing. Now if you have this thing, can I say that this is a connected graph?
Yes.
Okay, now this is a connected graph, and this is obviously an undirected graph. Now let's put directions here. If I'll put directions here, now you'll have to check what's reachable from there. Do you think this is now strongly connected means in this directed graph, if you can reach every vertex from every other vertex, then we say that it's strongly connected in a directed graph.
No, no, it's not strongly
Okay,
connected.
let's come to that later. Let's just discuss the definitions first. Strongly connected means in a directed graph. That's the terminology used for directed graphs. If you have a directed graph, then we say it's a strongly connected graph if from every vertex you can reach every other vertex. And we say it's a weakly connected graph if ignoring the directions of your graph, you can reach every vertex from every other vertex. That means a directed graph is called a weakly connected graph if you consider if this is a directed graph, right? If you ignore the arrows here, that means if you ignore the directions and it turns out to be a connected graph, then it's a weakly connected graph. Is that okay? So do you think this is a strongly connected graph? Let's just first discuss strongly.
No.
Which vertex
No.
can't be reached from which vertex?
Like
Actually,
we can't reach V5 from V1.
V4.
Can't reach V5. Yeah, right. You can't reach V5 from V1. So that means this
V4.
is a yeah, V5 also you can't reach,
even
V4 also
ma'am,
you can't reach.
we cannot reach anything from V3 in a way.
Yeah, you can't reach anything from V3. That's also right. So, and what about weakly connected? Do you think this is a weakly connected graph?
Yes, madam.
It's weakly connected because we already checked that it was a connected
Yes,
graph,
ma'am.
ignoring the directions of this graph. Okay, so that's the definition of strongly connected and weakly connected graphs. Then you have one second. Then you have something called components. So components of a graph are basically uh, the maximal connected subsets. Maximal connected, what do you mean by maximal connected? Or you can say maximal connected graph from a vertex. So let's just have this one only. And this one's not a very nice example for this. Let's take this V7 and let's have a V8 here. So if you have this thing, and let's ignore the signs for this graph for now. So connected graph means you know what a connected graph is like, where you can reach every vertex from every other vertex. So we know that this is not connected, right? This entire graph is obviously not connected, but there are components to it. Components in the sense this entire thing is connected, right? If you look at this thing, then ignoring the directions. If you ignore the directions, this entire thing is connected, right? And this entire thing is
Yes,
also
ma'am.
connected. So this
Yes.
is called a component, and this is called another component. So these two are called the maximal. Now, if you will take this one, V1, V2, and V3. Now, this is also connected, but this is not a component. So component is a maximal connected collection of vertices. So this thing is not a component in this graph because it's not the maximal connected set, but this thing is, right? Is this clear?
Ma'am, what is maximal?
No, ma'am.
Maximal
It is not
means,
clear. Like,
okay. If you start with this graph, component is maximal connected collection of vertices.
Means a maximum cardinality of edge, right?
No, not maximum card. It has nothing to do with the cardinality of edges and all. You just have to collect vertices. So you start with V1, and then you collect all the vertices that are directly connect that can be reached from V1. That will make a connected graph with V1, right? So you start with V1, you put V2 here, we can put V3 there, ignoring the directions. I've already mentioned it a lot of times. Ignoring the directions, you can reach V2, V3, and V7, right? So this is a component. Why? Because it's maximal. Now you can't reach anything else. Can you reach anything else from these V1, V2, V3, V7? Can I add something else to this one?
No, madam.
no.
That means it's a component. Now, if I do V1, V2 only, this is also connected V1, V2, and let's do V3 too. If I'll put V3, this thing is also connected, but this is not a component. Why? Because you can also add V7 here, right? That means it's
So,
not a maximal connected collection. Is that
so
okay?
it's like a superset and subset, right?
Superset and subset of what?
The vertices of the connected graph.
Yeah. This is the subset of the collection of all the vertices. Obviously.
Okay.
Okay. So this is called a component, and this is the other component.
Ma'am, suppose there is one vertex which is not connected from this graph, then
Let's say
that
V9 here.
that alone, this vertex V9, can we call it
Yeah.
a component?
Yeah, it's a component, right? Because if component means if it's already now V9, this thing is obviously connected, right? Because there is no other vertex to check the connectedness. That means this set is connected. The only problem is that it should be the maximal connected set. So you can't add any other
Okay.
vertex to keep it connected, right? That's why it's a component. But you can't take V7 alone because V7 is a part of this entire thing.
So,
It's
ma'am,
connected to a lot of,
V9 separately is a component you are saying. V9 vertex is a
yeah.
separate
If V
component.
Yeah, if V9 is alone, it's not connected to anything, this is a component. So there are three components now. This is first component, this is second component, and this is third component.
For the undirected graph, no?
Yeah, this entire thing was for undirected graphs. For directed ones, you just check the reachability and put them here. Is that okay?
Yes, ma'am.
Yes, madam.
Okay. Next up, we have cycles. So in cycles, cycle is basically this thing. So if you have three vertices and it's a closed thing here, that means the definition is that you start with a vertex and the only vertices, so it's a closed thing. First is it's a closed path. You know what a path is, right? We discussed what a path is. So it's a closed path, and only the starting one and the starting and the end vertices should be repeating. So if this is A, B, C, then this cycle, this is an undirected one. And if you have, okay, this is an undirected one. So you can have A, B, C, A. Now this is a cycle, right? A to B, B to C, C to A. This is a cycle because this is closed path and its starting point and ending point is same. So that's a cycle. Now, if I have a directed thing, let's say I have A B to C, and then C to A. Now this is again a cycle, right? A to B, B to C, C to A. This is a cycle. But if I'll take this thing, A to B to C, and then this thing. Now this is not a cycle, right? Is this okay?
So in directed graph, the cycle should be complete if it start from there and it's end from there in a way.
Yeah. You can also have this thing. Let's say you have this. There's D, and you start from A. So if you take A, B, C, then D, A, B, C. Okay, let's take something else. Let's take E here, and you're doing A, B, C, E, and then you're going back to C, and then you're going back to D, and then to A. This is also a cycle. It doesn't mean it just have to look like this, a polygon, or this. Is that okay?
Remember, we should have direction also. This you have said it for non-directional, na? A, B, C, E, D,
Yeah,
A.
this one is for non-directional, this one.
Okay.
This is
And we
obviously
can
a
add direction
non-directional graph,
also
right?
and make it like that. For the directional graph, we
Yeah,
can
you
make
can
it
add
like that.
direction A to B to C.
But the
Then,
direction should be in that order in a way. We can say that.
yeah.
But I mean, this A, B, C, C, D, A should be walk, right? Not path, because we are repeating the vertexes.
But that's fine. This is considered a cycle.
Okay, okay. Even if it is a walk, it is a cycle.
Yeah, it's a cycle. It's considered a
After
cycle. Yeah, what?
Yeah, so after like going visiting E, then we go back to C, and then we go back to A, and then
You
A,
can do that. And you
D
could
to
do
A.
this. Yeah, you can also do this thing. A, B, C, and then D, and then A. This is also a cycle.
Ma'am, just in the
Okay.
last case, just in the last slide, this V1, V2, V3, V4, V7, this group of it, we call it component, and the whole group of it,
Yeah.
we call it component, na, ma'am?
Yeah, this entire thing is a component. This entire thing is a component.
Okay. Okay, ma'am.
And you have acyclic graphs. So acyclic graphs, I'm not writing all of this. So acyclic graphs are the ones that do not have a cycle. So if you see a graph that has no cycle, like this thing, if you have something like this, then this has no cycles, right? Because it's nowhere closed. So this has no cycles. That means this is an acyclic graph. And coming to a tree, the tree is a minimally connected set in the sense. Now have a look at this thing, right? If you have, let's just do tree with an example. Let's say you have this thing, and all of these are vertices. This is a vertex. All of these are vertices. So if you have this thing, then this is not a tree. Why? By definition, your tree is a minimally connected set. So minimally connected set means a connected set which is minimal. Minimal in the sense, if I'll remove one edge from that tree, it won't be a connected graph. So minimally connected means that's the definition of your tree. Minimally connected graph. Minimally connected graph means if I remove one edge from there, even one edge, then it won't be connected anymore. That's what you mean by minimally connected. So if you have this graph, if I'll remove, so is this a tree? Because if I remove this edge, it's still connected, right? That means if I remove even now this, if I'll take, now this is a tree. Why? Because now if I'll remove even a single edge from here, no matter which edge I remove, even if I can find one edge which when removed from the graph would make the graph disconnected, then I say that it's not a tree. Like if I'll
So it
remove this
becomes
edge,
two components.
what? Yeah, then
So
it'll
it
have two
becomes two
components.
components. Yeah.
So if now this is a tree, why? because if you remove this edge, then this becomes disconnected. If you remove this edge, then it becomes disconnected. But if you will have this, then this is not a tree, right? Because you can still remove this edge and this is still a connected graph.
But if we remove the right side, then it could not be connected, na? So just add that, the last thing that you added, ma'am. Just the last line you
This
added.
thing,
Yeah, and if we just subtract the right one, just the far
this
right
one,
one, the far right one, ma'am.
this
Yeah,
one,
ma'am. Yeah, ma'am.
yeah.
So if we remove that, still it would be a tree. Yeah, ma'am. So it wouldn't be a. So
What
this
we
is.
mean by a tree is, that's why I said, if I remove any edge, now you don't decide which edge will be removed. You can choose any edge from here. There should be no edge which I'll then remove. The graph will become disconnected. So if removing any edge means any edge, not just this one. If removing any edge results in a connected graph, then it's not a tree. Is that okay? That means if you have this thing, this is not a tree because I can remove this edge. I have one edge which I can remove, and this is still a connected graph.
Ma'am, but if we remove the right hand side one, it won't be a, then it won't be connected. So
Yeah, if you'll remove this thing, this is not
yeah,
connected.
yeah, ma'am.
That's why this is a tree. Because this is a minimally connected set. Even if you remove a single edge from here, it won't be a connected graph. That's why it's a tree.
Madam, like the tree will have the edges and vertex together, right?
Yeah, yeah. It's this thing. This entire thing is called a tree.
Okay.
The graph is called the tree. Minimally connected
Yes.
graph.
On acyclic graphs tree,
What?
are all acyclic graphs tree?
Yeah, acyclic graphs are trees. Because when you don't have a cycle, cycles are the main problem because that's when you repeat things, right? So if you have if you have no cycle, if you will put this thing here, then that's the problem because this edge is the extra edge here that we don't need. The edge that closes the cycle is the unnecessary edge, right? Unnecessary edge in terms of connected graphs. We don't need that. So this closing edge, if you'll put one more edge to this, that will be the closing edge for a cycle, right? That closing edge is what's causing what's causing the problem here. That's why it's not a tree. Is that okay?
Yeah, ma'am.
Okay.
It's a tree, na, ma'am. What we have
This one
drawn.
is a tree,
Yes, ma'am.
and this one's also a tree. Okay. So
Ma'am, one thing when you were discussing the components
yeah,
in above, uh, we discussed non-direction one. We didn't discuss the directional one, I guess. Here.
yeah, but it goes the same way. What we do
Okay.
here is in the components here. Here we were ignoring the directions. That's why it became easier for us to write out to figure out the components. Now, if I start from here, I'll have to check which vertices are reachable from V1, right? And then I'll have to check, like, let's say you have V2, V3 here, then I'll have to check the reachability from V2, if something is reachable from V2, it's obviously reachable from V1 too, right? So you don't have to do that. So you'll have to check the reachability from V1. Now that would form you can directly use the BFS thing here, BFS or DFS, whichever you want to. You can use BFS and DFS to construct a component, right? If you have to find a component, how do you form a component? You start with a vertex and write all the vertices or maximum number of vertices that can be reached from V1, right? All the vertices that can be reached from V1. And BFS exactly does the same thing. So you can figure out the components using the BFS approach or the DFS approach. Is that okay?
Yes, ma'am.
Okay. So like in the previous example, the one that we did in BFS, DFS, Now here, that means this thing is a component, right?
Already 10:30, ma'am. Can we continue in the next
Yeah, yeah.
time? Like,
Okay.
if it is okay.
We'll continue this thing tomorrow. And okay, we'll end the session here.
Okay, so ma'am, we'll start where you have left today.
Yeah,
So
we'll start
we'll
from there.
continue tomorrow.
Okay. Bye, guys. Thank you.
Thank you, ma'am.
Thank you,
Thank
ma'am.
you, madam. Bye bye.